Okay, everyone. We'll just wait for a few minutes and then start. So, um, if you have any questions in the meantime, feel free to ask.
मैंने म्यूट करके रखा है।
Okay, I guess we can start. Uh, I'm audible, right?
Yes, sir.
Okay, great. Uh, okay, so I'll just add that. Uh, yeah. Okay. Uh, yeah. So last week we saw, I'll just recap what we covered. Is that the very basics of C++. C also has some portions also. So we wrote a hello.cpp file. Okay, try to compile it and run it. We saw about header files, including header files, custom header files like add.h. You can also include header files which are already included in the STL, so the standard template library. Other than that, you can have ifdefs, macros. Okay, very basic commands like very basic data types like built-in data types, the integer, double, bools. Okay, you can have scopes, different scopes. So this is a local scope of main, right? So this P itself is local, but the P here is global scope. Okay, so specifically access it, you can use double colon P. Did I give an example here? Maybe not, but that's okay. Oh yeah, oh, I did, yeah, yeah, okay. So you can use without any namespace. So basically, the global scope itself doesn't have any namespace. So you can use that nameless namespace, sort of, you can say, and then access the global variable. We saw about macros, like let's say adding to functions, uh, sort of equivalent thing. Function also, sort of equivalent thing of that, and yeah, custom namespaces. Okay, so namespace is sort of like you are collecting a collection of functions into a name, a specific name. So that's how you make a namespace. You can create functions. We'll also see like classes. You can have those also. So yeah, you can do various other things. Other than that, yeah, it's basically like you have a main file you're trying to compile, and then you're trying to compile different CP files and include the header so that the function that you're trying to call exists somewhere is what you're telling by adding the header file. Okay, so yeah, we saw those things. Again, subtractor dodge, yeah, so you can have a very similar example with add. Yeah. Just to mm, just so you guys know, usually there is a main.cpp file. This is just a standard thing. uh, you can have any custom name, that's okay, but you definitely need to have the main function. Okay, so this is the first thing that gets called, even if you have different CPP files. Okay, so you have add.cpp, hello.cpp, let's say the file 1, file 2, file 3, like n number of files. But the first file, any of them must contain main function, which gets called first, and then subsequently everything else, whatever it calls in. Okay, right. That's sort of the idea. So let's look at a little more into STL, like some of the stuff that you guys should know. Okay, so let's look at the vector header, the vector class actually. We'll be covering classes in more detail, but just so for completeness, I'm mentioning it's a class included inside the STL library. Okay, so as usual, I'll have the IO stream to print stuff, and furthermore, I'll include the vector header. Okay, so this exists inside the STL and something we'll be using a lot. Okay, uh, here I assume you guys know about a data structure called list. Okay, so the idea is that I'll recap it anyway. So the idea is that list is a data structure like list assumes contiguous memory layout. What does that mean? It means that let's say I want to store some 100 or n values of something. Okay, when I say something for clarity, just think that it is inbuilt data type for now. So something like, let's say, integer or float. Okay. So if I have to store 100 numbers, okay, be it integers or floats, I'll allocate memory for it, use that, and then deallocate memory. Uh, that is sort of the basic idea of it. Okay. A list is essentially this abstract idea of this data structure. Okay. And an implementation of such data structure of this list is inside this vector class. Okay. That's what comes in with STL, and we'll be using that. Okay. So I'll decide uh, size. Okay. So size will be 15, I think, let's say. And then I'll declare a vector. Let's say, okay, I need to pass the template. We will be learning about templates also, but just for now, know that I'll be just dealing with integers. So you have to pass it within this single angular brackets. Okay. So the standard vector class. So with the namespace standard, you have to put that. Okay. Class name vector, and it's a templatized class. So you have to use int. So you pass in int inside the template and give it a name. So I'll just call it A, and I define the size. So I'll just define the size here. I'll pass the size here in during the construction. Again, constructor and destructor will cover in more detail. But just so you guys know, this is the syntax for declaring a vector. So standard vector, integer, with, let's say, the name of the vector is A, and then the size. All right. This pretty much declares a vector. And here there will be 15 numbers. So because I chose 15, you can store 15 integers together in a contiguous layout. Okay. So the way it works is it starts from a starting address in the memory, and then assume that integer is 4 bytes. Okay. So it will allocate 4 times 15, 60 bytes of memory. Okay. So from the starting, first 4 bytes is for the one integer, one number. Okay. And then the next, and then the next, and then the next. So 60 bytes of block of data will get allocated. And the nice thing about using classes like this is that you don't need to manage the memory. It automatically gets managed for you. Okay. More details on that. What is this management of memory? I'll discuss more in later. Okay. Let's just see how to. Any question? Yeah. So let's see how some of the methods or the functions which is built into this vector class, or which are very useful also to call. Okay. So this is one way you declare the vector. Okay. Other way you can do is declare the vector. Okay. Let's say I call it B. Okay. But you don't give it any size, right? Uh, so then what happens is you actually don't have any memory allocated for this vector, essentially. Okay. So there are two ways to do it. You can pass the size during the construction so that you get the block of memory for it, like A has. But you can also do it this way. You do not give it any size, but just say that there is a vector of B, which currently doesn't have any memory allocated, but I want to resize it later on. Okay. Hence, there is a useful resize function, which you can use. Okay. So, and then let's say I give it the size, or maybe I'll just pass a constant number like 10. Okay. So passing 10 to it makes this vector B of size 10 integers, and A is 15 integers. Okay. Furthermore, you can actually resize it as many times as you want. Because A is already constructed with 15, I can resize it to be 10. Okay. It's essentially the same vector that we're referring to, but now it does not contain 15 integers. It will contain now 10 integers. Okay. And you can keep going. You can reset it to 10, 20, 100, anything. Okay. The thing to note here is that to know the state, as in how much size you currently have in a vector. Okay. Let's print that first. So a size, I'll just call it a dot size. Okay, so you call the function dot size, and then you just access it. Okay, so one more thing maybe I should mention it here. To access an object's inner functions, we use the dot function. We'll cover this in more detail, but just so you guys know, A is an, so this is just I'm mentioning for completeness. In the namespace standard, in the vector class, templatized vector class of integers, okay, the object A is created with constructed passed as size, okay, and similarly everything here, namespace standard vector class is created, templatized vector class integer of integer vector is created of B. So A and B are objects, and to access the objects inner functions, we use the dot function. Okay, like, and size is the function, and as usual, functions usually have this syntax. So you have these two brackets, small brackets. Okay, then yeah. So this is something which will print the size. Oh, sorry for that. Yeah. Uh, Let me. Okay, then let me try compiling this thing. So should be okay. Then we'll save it. Okay. Yeah. Um, I see. I'm back. Yeah. Okay. So size is 100. So this is 100 because the last resize that was done on A is 100. Okay. So hence it prints the size as 100. So it's a very useful function if you want to query what's the current size of the vector you're working on. Okay. Useful function. Another useful function is the capacity. Sorry about that. Not something you need to usually worry about, but just so you guys know, the reason to have this or this sizes, I'll just print it first so you guys know. It usually is for small numbers the same, okay? But there is, it again depends on the OS and the number of the size that you're working on. So this absolute number of this value, so 100 or 10 million or 1 trillion or whatever, size is actually the accessible area of your vector, okay? But because of performance, it might actually allocate more memory. I'll repeat that. So size is the actual number of values you can store in your vector, okay, and you have access to. But the capacity is the total size, which is usually again will be more than the size, but that is what is already allocated for a vector anyway. Yes, you can't access it right now, but if need be, you can. It will reallocate. It will grant you that access. Now, why is that? The reason being, each time you do this resize, okay, the memory block in some place in your, let's say, RAM, okay, these are CPU codes. So let's say in your RAM, CPU RAM, like RAM, which is the memory, there the memory first gets deallocated, okay, whatever is the currently allocated memory, then it gets resized to 10, as in there's a new block of memory which is requested, and that memory gets allocated to your vector. Okay, this is a very expensive operation from perspective of operating systems. Okay, so performing resizes multiple times again is not a good idea from performance perspective. So there's an optimization which is done where if you request for some certain sizes, it might actually allocate more memory than we are requesting. Okay, so that if you require more data later on, right, it will just give you the memory which is already allocated to you. Now you can access that memory. So let's say you request of 100, but the capacity was 200. Okay, and you again resize it to 150. So the next 50 values, which is already allocated for anyway, is just available to you right now. Okay, You might not see these numbers being different in small values, but you can feel free to try for larger values. Okay, all right. That's sort of the idea behind the size function and the capacity function. I hope that is sort of clear. Okay, we'll go into more details on this memory allocation a little more. But before that, let's see some more syntax as to how to access this vector and work with it. So I'll set I to be 0. One nice thing you can just do is a dot size, so you don't need to worry about what's the current size of the vector. So you can start from the 0, go till the size -1, okay, and do I plus plus. Okay. Uh, Furthermore, you can do, let's say, a of I. Uh, Once again, is I, and then let's print out the vector. Okay. All right. Let's compile and see. Nice. So the vector is of size 100. So it starts with 0. Okay, so that's what we fill it with. So we are filling the ith position with the ith value. A very simple code where the 0th value is 0 and keep going, and then 100th value is 99. Okay, right. One thing I would like to bring to your attention is that this is uh, essentially a dereference operator combined into a bracket operation. Okay, what I mean by that is a little bit about pointers. Okay, so these, like I said, the data structure of vector is a list, right? So technically speaking, if I know the starting address of the vector, I can access any ith element from it. So to do that, you access the data. So the data function itself is also again a useful function where it returns the starting pointer to the vector. Okay, so this gives the starting pointer. And the nice thing is, because of pointer arithmetic, you can just add I to it. So what this will do is, because it knows the data type of A, which is integer, how many shifts it has to actually go in bytes. Okay, it automatically knows. If I add I to it, so it's the first 4-byte shift. So at every ith position. So if I is 0, the first position, which is, let's say, maybe I'll give an example. So let's say, sorry about that. The pointer memory looks like, let's say, again, this is again an example, 0x some number like this. Okay, so this, let's say, is the starting position of your vector. So plus 4 bytes. Okay, so 4 byte, again, this is in hex, so whatever equivalent it will be, I'm not going to write it, but let's say, so plus 0 will just have this guy, plus 1 will add pointer 4 bytes to it, okay, in the memory, and access that position. Next one will add 8 bytes to it, and so on and so forth. Okay, so every multiple of 4 bytes, okay, will get added to this initial one automatically, because it knows which how many what's the size of your pointer starting. Okay, so this is something called pointer arithmetic. It automatically does that. So to access the ith element, you just add I to it, to your starting pointer. Okay, but we did access what we did is just access the pointer or the address of it. Okay, now imagine this way: your address itself is some position only. Now the pointers has a memory data has a data type associated with it. In this case, it is integer. Okay, so let's say this finally, after all this addition, it goes to something like this, something like this. Okay, this is some position. Now this position, if I want to read a value of it, okay, I know it's an integer. So what I will do, I mean, again, the OS or whoever, right? What it will do is, since it knows that this is the position, from there till the next 4 bytes, it will read off the integer, right? Because I know my data types are integers, and I know the starting address of the position I'm at. Okay, right? So just a dereference will take care of that. So actually accessing the ith position that way. Uh, okay. Okay. All right. I hope this part is clear. What we're essentially doing is starting from the starting pointer, we're accessing the pointer of the starting of the vector, going to the ith place. Okay. Then after going to this is in the pointer or the address domain, if you want to think in that way. Then again we're going back to the accessing the value in that address. So the dereference operator or the star operator does that. So after doing this, you can just write it again, iterate. So essentially this whole block, okay, I'm writing sort of an equivalent to it here. Okay. This whole thing is essentially what this bracket operation does. Okay. The nice thing is that you can always do it in pointer arithmetic, nothing stops you. But there's a nice useful function given to you by the vector class for you to do it. Okay. And this anyway, you can do it the same way and replace the same text here with this. Okay, I'll just comment this for now so that doesn't repeat and you get the same, see the same output. Okay. All right. That's yeah. As you see, it's the same output that we get. Okay. All right. So that's sort of the idea behind vector. Okay. And then I can go with that. Okay. Let's see about the stack allocation and heap allocation. Let's say yeah. Okay. For using this, I need to include the array header file. Okay. Also include the IO string because we want to print stuff. Okay. And then let's write the main function. Okay. Uh, the difference between the vector and the array is the memory allocation location. Okay. So vector gets heap allocated, arrays get stack allocated. What does that mean? Okay. Let me give you the syntax first and then explain further. So again, the array class itself is also in the standard namespace, also templatized, but this time it does not take only a single parameter. It also takes multiple parameters. Let's say integer of 10, okay, and 5. So you have to, during compilation time, okay, you have to specify what's the data type and how many values you're actually allocating. This is in contrast to vectors where the sizes can be dynamic. Okay, again, this is also called dynamic memory allocation, and this is called static memory allocation. Okay, that's the job of uh, that's the job of stack allocation of arrays here. Okay, stack. Um, so if you see this array is the implementation of, again, it's also a list. Okay, it's very similar to vectors, a contiguous list of data, but the difference is that the here it is like compilation allocated. Okay, so it knows the sizes at compilation time, and you cannot change the sizes. Okay. Uh, so yeah, let's say this is A. Again, I'll just give it a name A. And if you want to access values, you can again use the bracket operation, very similar to this one. You don't have to really change anything. Okay, so let's do that. And yeah, that's pretty much it. Yeah. Now, what's the actual usefulness here? Or I'll have return zero. The return zero is only for because to return the main. Okay. Uh, let's run the array dot cpp file. Okay, so it prints still 5 values. Okay, that's the sizes. Now you might ask, why do we even care about sizes at compilation time if we can always pool of memory? Okay, so if your work project or whatever problem you're working on requires you to have larger pools of memory, you can always dynamically allocate that memory, use it, and then discard it. Okay, as we saw, doing a multiple resizing itself is expensive, so that is that's another issue. The uh, main thing to remember about uh, heap allocation or dynamic memory allocation on RAM is that it is slower, okay, compared to something you're accessing from the cache. So cache is the fast memory in nearby your CPUs, and when you have stack allocation like this, that is usually done on the cache. And because the sizes are known, get it can take some it can allocate that memory, okay, and the access to this data structure here is much faster. Okay, all right. Any questions? I think this part should be clear. So arrays usually you use it for stack allocation, and vectors you use it for dynamic memory allocation. There's definitely an advantage to using arrays, but as you can maybe probably guess, because of the larger pool memory of vectors, that's something what one wants to use. The downside of stack allocation is that there is a limited size of stack. Okay, and that is something which is sort of you can think like it's fixed. Okay, there are ways to change it, but then again, limiting to the default is usually the best. So here, passing like 1 trillion or maybe a very large temp power, maybe 50 or something, it's not probably the best idea. I'm not sure if there's enough memory in the world itself to accommodate that, but again, not certainly not in the cache. So that's in those cases you actually run into errors, which are the stack overflow issues. You might have maybe heard this before. So that's one that happens. You are filling up a stack with so much request of memory that it actually can't provide you that much memory. Okay, so yeah, that's something to keep in mind. Cache or stack allocation, fast but limited in memory. Vectors, slower than compared to cache, okay, but larger pool of memory. Okay, so and to access these two data structures or implement them in C++, you can use these two you can use these two classes, arrays and vectors. Okay, so yeah, mm, that's one. Let's see the yeah. Let me make a oh, sorry about that. Include the array header. Okay, also the string because always we want to print stuff. So what we saw is the C++ way of allocating arrays and the vectors. Okay, so this is something also you might have seen. Also, one can do. So let's say I do 10. So this is also a stack allocation, okay? But this is a C way of allocating arrays, okay? With using arrays or vectors, you make the intention clear, okay? As these two data structures or these two classes itself exist, okay? In C, you can just do it this way, okay? Just uh, so just so you guys are familiar with the C syntax also, I'm just showing you. You can do it multiple ND array also, okay? So you can do it this way. So make D to be, let's say, 7 here, okay? And let's make C, this will have 8, let's say. So this is essentially a array of 10 integers. This is 10 by 7 matrix. And in higher dimension, you can just think of a tensor, 10 by 7 by 8. Okay. So this is one the array, the 2D array, the 3D array. Okay. To access these values, yeah, okay. So one thing I'll maybe just clarify now, it might be little basic, and because we're in the initial class, so just covering some stuff which you guys should be familiar with. But maybe today or the next class we'll be starting classes, the basics of object-oriented programming. Okay, and then using those concepts, we'll be building on different um, concepts on top of it, which are key to the modern C++. Okay, so yeah, if things are familiar to you, so yeah, please bear with it. Okay, so let's say I have first is 10, so I'll just put 10 here, I plus plus. Okay. So I don't write anything, but okay, maybe I'll just do that. So I'll access the I, J. There's no second value for now, so let's just do it this way. Fill it with I. Okay. Now what we'll be doing is fill all this 1D, 2D, and 3D array in the sequence of the actual memory access, and fill each position with the ith value. So what I mean. So for B, I'll need J index. Uh, So yeah, B. Okay. So B requires my bad. Requires two indices. So I and J. Now the second index is 7. Okay. Right. So I iterates over the first this dimension, first dimension, and J iterates over the second dimension. Okay. Now something to keep in mind, even if you make arrays which is 1D, 2D, 3D, or n dimensional, doesn't matter, you have a certain structure in which any of these things are arranged in the memory. Okay. Essentially, it is also a list. Okay. It might be an ND array, but it is a list. So what happens then in that case is there is a certain order to which these values are stored, which means the first 10 values are stored for A. That's it. So that is, I think, clear and straightforward. But if you have the stack allocated array B, okay, which is 10 by 7, first the values of 7 are stored. Okay. So the way C at least follows is the row major order. Okay. Where first the rows are filled. Okay. And then the column in this matrix way, in this matrix, and so on and so forth. So the way to remember is the rightmost index gets filled first, then the leftmost, then the leftmost. Okay, then the left, and so on and so forth. So in this case, if I want to access the ijth element, okay, and I want to put the ijth element as the I and jth value. Okay, so which will look like this. So I plus, oh sorry, j plus. Okay, so because j is the this is something called the fastest index. So the way the fastest index goes is from the right to the left. Okay, so my j index is iterating over here. Reason being, I just put till the size 7 and I chose it to be 10. Nothing is that these are dummy indices. You can name it any way you want. But the point is, if you're accessing ith element and jth element this way, so the way to write it is this. So I times, then you put in the size of j, this 7. Okay, let's print this and see. The, okay, let me just copy this. So this will have and see out a of I. Okay, right. This should print it. Okay, that's good. We need NDR. Oh, not bad. This should make the formatting a bit better. Okay, so A gets printed from 0 to 9. That's as expected. But what about B? Let me just comment this so that we only get the output for B. Uh, print this B. To access B, I need this point. And this. Okay, so it is 70, like 10 by 7. So 70 numbers should be there. So from starting, if you see, the way I'm accessing these values, it starts from 0 and all the values are there. Okay, I'm accessing till 7. Okay, so ideally, if I even if I switch this, they should not matter because oh no, it actually does. Sorry, it prints the jth column first. So if you iterate over the array, ND array, in the sequence in which it actually gets stored, okay, then you get the array in this order. Now, the thing I want to definitely mention is that there's a trick to it. How to so this is sort of you can think like you're linearizing your matrix. Okay, the way you're accessing it is first you're accessing the first column, then the second first row, then the second row, and then the next row, and then the next row. Okay, to linearize in this way, okay, to or to index it, there's a trick you can use. First, write the fastest indices. Okay, so let's say you have. Okay, I'll take example of C to explain this. That will be better. This is fine. Okay, maybe let's just take this. Yeah. You actually don't need the brackets here. The last one just needs it. So, but for completeness, you guys can write it. That's yeah. Okay. Let's use this one and comment that. So for C, I need another index. Okay. So let me call that as K. And if you see here, it's 8. So I need to be careful to put that here. We'll have ijk, okay, ijk, j. So the indices are the way it goes is first is fastest index is k, then you have the next fastest, which is j, okay, then the next fastest, which is I. Now, after you write this order, the way to multiply, like you have to multiply this coefficient, right? Because I wrote here, okay, it's nothing. There is no other index, so you don't have to multiply anything. For j, you multiply with the size of k. Just do that. It will work. So size of k, okay. And with I, you multiply it with the size of whatever is left to it. So j times 8, which is size of j times size of k, okay. So here in this case, it will be size of J7 and size of K, which we have written as 8. That. All right, we're done. So now if you use this, okay, you can linearize any n-dimensional array with this way. Okay, let's compile that. Did I make a mistake? Um, oh, my bad. It should be C. Okay. C is the three-dimensional array. Okay, compiles perfectly. Let's print this. So I need C. Oh yeah, I should have written ij here. Okay. Then ij, that's okay. C, this whole thing. Let me add this. Awesome. It starts with, as you can, I mean, well, it is the numbers a bit. That's okay. I think you can see this. Starts with 0, goes till in a linear fashion. Okay, goes till 559. So 560. That's product of 8, 7, and 10. Okay. Oh, yeah. Last time people did say this one, so I'll increase the font size. Okay. The way to, again, the 3D structure might be a little harder to imagine. To imagine this two-dimensional array, think of it like, okay, maybe I'll just do it this way. So think of a matrix which is like 1, 2, 3, 4, 5. Okay. And then 6, 7, 8, 9, and 10. These are the positions. And even if they are the values, it's the same. You can imagine it however you want. So this is a 2 cross 5 matrix. Okay. And a ND array like this is essentially that. A 10 cross 7 will be like you have 10 columns, 7 rows. Okay. And because this is the notation what C follows, okay, which is 7. Okay. So as in C follows row major format. So the 7 dimension, so which is the last dimension, that gets filled first. Okay. So imagine having 7 values here, which is let's say 6 and 7, and then starts with let's say 8, 9, oh, some of that, 10, 11, 12, 13, and 14. So 7 values in each row. Okay. And then the next row has 2. So imagine like 10 such rows are there because we have 10 here. The first is that this value, this row gets filled, and then this row gets filled. Okay. All right. The only way, the only thing difference here is that the actual filling of this ND array, okay, does happen in a contiguous fashion where 1 to 14 values are filled together. It's just that for our visualization, we are treating it as a 10 cross 7 matrix. Okay, that's it. That's the only difference. Okay. Now, that is sort of the idea. Okay. Now, imagine this doing the same thing. Okay. But with a C++ format. Okay. There, what we'll do is you will, these are small values. Okay. I'll use the array. Okay. So, standard array, integers. Okay. And let's say the total size is how much? 70 for B. So let's do that. Let's make a linear array itself. Um, I'll call it B CPP. Okay, the C++ way of doing things. Okay. create that, fill it. Okay, okay, this is a question. Yeah, can ask. Okay, so what you can do is you can start with 0. Okay, and iterate till I less than. Again, I don't need to worry about what size, so I can just use this dot size. I know it will be 70, but yeah, I can make it more generic this way. I plus plus. Okay, then TCP of CTP. This one I will access the ith element. Okay, set it to I. I don't need to worry about the linearization here. Okay, yet. Okay, and then just print it. So this will have, so this will be this guy. You just need one index for even a two index array because we just linearized it. In the actual implementation in memory, okay, the OS essentially does the same thing. It has it in a linear form. It's just that for visualization from our coder perspective, you have it as a 2D array or a 3D array or an ND array. Okay. And print this also true. Let's comment, sorry, comment this, then have, yeah. All right, so prints the same thing. Okay, so B uh, in the CPP array format also prints from 0 to 69. Okay, right. Very similarly, you can just repeat the same thing for the very okay, in a way difficult to imagine C where the product is, I think stands for, yeah, for 60. Okay, so you can just have this way and repeat the same thing. Essentially, there is pretty much no change in the code. Okay, so except for these. Okay, so all right, it prints all the values. Okay, I just printed this also, so I will just comment that to see. Yeah, so you see it starts with, oh, starts with 0. Yeah, yeah, and then goes in a linear fashion because anyway this linearized to be of the correct size, and then yeah, there we go. So essentially, what we see is that the C++ way, it does not inherently provide you a ND array, but because it's all about visualizing the same data structures and same data in a different layout. Okay, that's what I want you to guys to focus on. Okay, this is two ways of two different ways of interpreting the same data or visualizing the same data. Okay, so yeah, this is yeah, essentially C++ does not allow you to make ND arrays. Okay, but then again, you can just create the complete memory first and then visualize it according to your use case. It could be 10 times 7 or it could be 2, 5, 7 are the factors. So it could be 35 and 2. Okay, that could be the different dimension, right? You don't have that freedom in when you actually declare it in this structure. Or but once you linearize it, you can interpret it in different ways, right? So 560 gives you more freedom. You can have 10 and 56 also. You can reinterpret the C array, which was hard coded to be a 3D array. You can actually visualize it as a 2D array if your problem requires it. Okay. I hope this is clear. Okay. And yeah, for linearizing to any index, you can use this trick. Okay. right? Uh, yeah. So let's see. So this was the stack allocation, pretty straightforward and simple. There is a way to do a heap allocation too in C++, like the pure C++ way. So let's do that. So I'll just show you guys the syntax for it. Again, need ISBN for it. You don't need to include any header files here because this comes from the, so there are default headers which are always included in C++. So the keywords I'll be using are inbuilt. So first of all, we'll declare an integer pointer a. Okay, essentially it's like we should declare the object of a vector class a integer. So it will be essentially a vector of integers or so on and so forth, right? Of a, right? Instead of that, we'll just uh, declare a pointer first and then start the main function. And that. To allocate memory, this is the syntax for it. So you use the new keyword, okay, and then integer of let's say 5. So you are actually how do I put it? Keep allocating 5 integers in the you're allocating 5 integers, and the starting pointer to that is stored in A. So this is what the syntax means. Okay, you can do this also. You can combine these two lines. You can write integer b, okay, equals to new. So the new keyword is essentially the allocation. Okay, this is what C++ does to allocate memory. The C equivalent using malloc and the corresponding uh, destruction. Okay, malloc and free. You can look up the syntax, but pretty much similar idea exists in C++, but this is a C++ way of doing it. So I'm showing that. So integer, let's say 20. Okay. Very similarly, we can write I0, I less than. We don't have any method here because A is not a class that we have access to its sizes, right? So A dot size or something like that does not work here. You have to actually specify the size because we selected 5. So we'll put 5 here and then I plus plus. Okay. A of I is, let's say, I times 3. Okay. Then on the loop where I is 0, I less than size is 20, um, I plus plus. So can just do this way. Say I times 2. I'll just print it. Then print B, my bad. Sorry about this. A. Very similarly, you can then print B also. But here it should be 20. My bad. Should be replied by. Okay. So A gets printed. So till 5. Uh, Okay. I request you guys to please mute if you don't have questions. Okay. Right. So A gets filled from for 5 values, which is each of them times 3. So that's what you see here. 0, 1, 2, 3, 4, right? Till 5. So 5 minus 1, 4. And 5 gets B gets filled till 20 for 20 values, each with multiplied by 2. Okay. So that's what we see here. So this is the way you actually use the new operator. Again, I did not do something here which should always do if you're using the new. Usually it's fine. Not, I wouldn't say it's fine. In this case, it was fine because it's not a very large amount of data that we're allocating. It's always a good practice, okay, to delete the pointer. Okay, so delete A, sorry, A and B. So after you work with your pointers, so you declared pointer A, declared pointer B, allocated memory for it using a new operator. Okay, and at the end, you must actually delete it. Okay, the good practice and this structure of allocating memory and deleting it is automatically taken care of by the vector class. Okay, there's a nice feature of C++ as to how does it do it, but we have to get through first learn about classes itself, then we can get through. Then we'll come to how does it do it. Okay, all right. So there's a lot of abstraction which is taken care of by useful classes like vectors and arrays. Okay. So when writing C++, absolutely make sure you use them. Yeah, definitely make use of them. Yeah. Okay. Now let me quickly mention something about the const keyword, and then we can look into the same idea of remember that. Yeah, okay, and look into the same idea of ND array, but in the vector sense. Okay. So okay, const dot okay. So first we'll include the IO string, and I'll make a integer. Let's call it p. Let's store the value 10 to it. Okay. Now, usually when you have a variable and you're passing setting it to some value, it needs to be in C++, you have to have a strongly like data type to it. Okay, while you initialize a variable, but if it has const keyword extra to it, it just means that this value of p cannot be changed. It has been set to 10. Okay, and that during the course of this complete program code run, okay, it won't change. That's what you are telling to the compiler. Okay. Now this has its own uses. Okay, so what you can then do is uh, use this value. Okay, like we used to set sizes, right, for vectors. You can sort of give the same thing to your arrays too. If I include the array header, I can access the array class. So array, then integer, then let's say p. Okay, right, and call it a. So or just write a loop. There are different, there are more modern ways of writing these for loops. They are called range-based for loops. But just so you guys maybe might be more familiar with the C way, so I'm just writing for loops in the old traditional C way. Okay, b a dot nice. Now we can use this because it's the vector class, sorry, the array class. Plus plus yeah, I is to I. Oh, and, um, Then just print in. Okay. It works and without any issues. The only reason it actually works is because the p value that we have, I can actually maybe just set it to size for more clarity, because this has been set to const. So let's say I did not actually did it. So you'll actually get an error that whatever template parameter you're passing, okay, has to be a const at compilation time. You can't change sizes later on. So making sure that it respects this behavior of for templates. Okay, so then we have not covered templates, but there's a thing about templates. They need to be constant at compilation time. Okay, so you have to pass a const value here, and then you can keep using it later on. Okay. Oh, another thing. Don't confuse with this size, which is a variable, with the function size here. Okay, they might have the same name, but they're two different things. Okay. Another thing, you can sort of do a macro for it. So you can set something like this, hash define. Instead of size, you can put like, again, I think I told you about this. So you put size here, it will replace the texts with the number 10, which you might run into some really bad issues. So you can put something like number like this, something like, okay. So, and use this macro every other place. So let's say I want to use this macro here. You can definitely feel free to do it, but there's a clean way that C++ provides. So you can just do it this way. Okay. All right. Okay. Any questions so far? Okay. Another thing about const. So there's a bit of pointer arithmetic one can do. Let's say I define integer p to be 5. Okay. Now I can define a pointer q. Okay, integer pointer. Oh, that's a good question. When do you need to use it? It really depends on your, again, I know the answer seems redundant now, that it depends, but yeah, it really depends. So each of them have their own strengths and weaknesses. If you actually need a data structure of yours, let's say a vector or list list type data structure, which needs a lot of data, you have to allocate for, let's say, some use case. For example, if you are in scientific computing, let's say you're storing a large amount of data for some, you're solving differential equations or something, okay, and you are dealing with vectors, okay, which needs a like a huge amount of data. You have to store them in, let's say, memory, right? So you use heap allocation in that case. Uh, yeah, like that. And if you know that your data is not too large and you can get out small values for faster speeds, you can go with stack allocation. Okay. Now, in general, yes, heap allocation should more or less always work. But if performance is the priority in certain cases, that's when you go for heap allocation also. Okay. All right. I hope that answers the question. Right. So what I'll do here is make the integer pointer q. So here the difference is that p is just a variable of data type integer holding the value 5. Q is a pointer to such an integer. Okay. To set this, what we can do is, Oh, sorry. So Q equals to uh, sorry, ampersand, which is the address operator, okay, of P. So what we're doing is taking the address of P and setting it to Q, because the address of P, okay, so Q is not, it's a pointer, right? So pointers store addresses. They do not store the value. Pointer itself, the variable Q, what it has is not 5. It has some, let's say, address which is in some hex. Okay, so let's say it is some 0x and something like this. Now, this address, okay, in the memory, actual memory, okay, will have this value. To access that, we dereference the pointer and access it. That's how pointers work. And always remember the value that Q stores, okay, it's always the maximum integer that you can store in your that your system can represent. So for me, it will be 64-bit integer. So the maximum value of Q is a 64-bit int. Okay. Now there's a nice way of accessing the highest integer you can in any system. So you can use the standard size underscore t. So equivalent is size underscore t. In C++, it is in the standard header file. Okay, you can just do that. So size underscore t. Okay, right. Uh, I hope this part is clear. Where p itself is a variable. Okay, now it is located in some memory location, right, which is holding the value 5. To access the location address itself, we use the ampersand operator, and that operator we store it in Q. Why? Because Q is the pointer, as in Q stores addresses, right? And maybe it looks something like this. We can actually do that. Maybe instead of giving this example, I'll just print it. So I can do maybe address of P. Okay, let's just print that. Okay, it is lost. Now you see that this is some hex value. Okay, hexadecimal representation where 0x16b1ee9f8 actually is the address of P. Do not be confused with the address of Q, okay? Because Q itself is also a variable. It has its own address, okay? Now, the thing is, Q itself is a 64-bit integer. Now, you might say, if it's a 64-bit integer, why do we have int, right? So the int here does not represent the data type of Q. I repeat, it does not represent the data type of Q. It represents the data type of the value at the address what Q stores. I know, sounds a little confusing, but I'll repeat. So Q stores the address of P, okay, and P is itself an integer. So the integer pointer declaration that you have is the integer. So int is hence the pointer for Q is integer. Okay. Again, because the address that Q stores, okay, is the address, it stores an address which is actually holding an integer. That is the data type that you have here. Okay. Q itself will always be of itself will always be of the size underscore t. For my case, it will be 64-bit integer. Okay. Let's print this two values and check for ourselves. Just so happens that, yeah, as you can see, these are two different addresses. Okay. Again, differs only in the last 2 bits because how the allocation works. Again, I won't go into more details for that, but just so you guys, what I want you guys to focus on is this pointer arithmetic, how pointers actually work. Okay, what we did is stored the address of Q, right? So now if I want to access uh, the value at Q, so I can do a dereference of it. So what it says is uh, Q has an address. Okay, so you go to that address, get the value of the variable there. How does it know from that starting address to how many bytes it has to access? It knows because it's declared as that integer pointer. Okay, all right. Yes, if you print it, yeah, so it gives you 5 because that's what uh, actually has. So now if I change P to be 10, okay, it changes to 10. All right. The reason being Q actually stores the address, the proper address of P. So if the value that contained in P changes, the memory address does not change. Again, that is what it'll get pointed to. So if we try to dereference the value, it'll just try to print the value at P, which is 10. Okay. All right. I hope that is clear. Oh yeah, one more thing. If you want to yeah, this is yeah, it's another important thing. What we had is was a const size, right? So again, this also has an address. So ampersand size is the address of size, right? Again, this is an integer. What if we want to store q to it? Q to hold that size, right? This is something which is not a okay. The reason being, you're trying to demote, okay, a sort of discard. Okay, that's what it says here. The size itself is const integer. And when you try to access like it has an address, you're trying to store that address inside Q. Okay, so the constness is sort of lost. You have just you have Q, okay, which is just an integer. Meaning, if you try to change the value, ideally you should be able to change the value at Q, right? Like whatever it's referring to, because that's what it's the integer pointer. It's not const integer pointer. Okay, so to prevent you from making this mistake of trying to change a value of a variable which is already const and should not be changed, this is not allowed. Okay, so that is something you have to remember. Not allowed. Okay, all right. I hope this is clear. Okay. Uh, yeah, it could be a network issue for you. I'm not really sure if uh, yeah, if others have faced this issue, so maybe they can clarify. But yeah, if this fixes rejoining fixes this issue, feel free to do that. Yeah. Okay. Let's extend the concept of vectors. Okay, we'll use those vectors, but now we'll make n-dimensional data structure out of it. Very similar to arrays here, which n-dimensional again were quite simple. But let's say I want to make an n-dimensional vector, we can always linearize it. That is always there. Okay, but let's see it in both ways. Okay. To get more perspective into how to use the vectors. Okay, I need the vector header file also. So name. Let's make the standard vector of integers. The A of size 7, and then B of Okay, let's do one thing because we'll be needing a lot of numbers. Let's define them together first. So let's say size m, integer m, okay, 5 and is 3. Can make like p 2, q as 8, and then r as 7. Okay, this I can then just call it as a single dimension, just let's say m. Okay, then so that's fine. Okay, so a is m, and to fill this value, I can just iterate in this way. I got size I less than, so the condition, and then I plus, which will be a of I, let's say equals to I. Okay, well, and straightforward. Okay, no comparison errors, so good to go. So let's just print it for seeing how the value it looks like. We'll have A as A of I. And line. Okay. So the compilation done. Value is also stored. So A is of size M, which is 5. So those values get added and printed. That's fine. So this was a single 1D array, but in a vector format. What if we want to make 2D array? Okay, 2D list, if if I may say so. So what you have to do is make a standard vector, okay, but instead of it storing integers, okay, then just make it a standard vector of standard vectors. Standard vector of standard vectors. Okay. Again, still that standard vector itself will also store integers. Okay. So this is the sort of the syntax for it. It won't be A, it will be some other vector B. So the way this one works is B itself is a standard vector. Okay. That stores standard vectors of integers. So this is basically like P itself is a is a container and itself stores a lot of these A's. That way you can think. So to do so to work on this, you have to take B, resize it to um, let's think this through. So it will be m cross n, right? So yeah, so this will be the outermost index. So we want it to be like, let's say, m cross 3, so it will resize it to n. Okay, then you have to have a for loop, which is, let's say, I. Again, it's fine if you have I again. We actually need two indices here, so we'll put it that way. I is 0. Yeah. I less than, we'll put the value later on. I plus plus, pretty similar, but we'll have the index j for it. And then b of, so the nice thing about this is that you can use the bracket operators. It will index, let's say, to ijk. So that's how we'll follow it. So j will iterate through the standard vector itself for integers, and the ith will iterate over the standard vector itself of whichever we want to look through. So this will be like again we'll use the index to linearize it. So it will be size of j and which is of this dimension and which we are putting it as m. Okay, and size of n is the b vector itself. So this will be size of m. Yeah, yeah. Okay, and then finally you just try to print this. So standard the out. Right. Yeah. B, and then this and yeah, here. Okay. So let's yeah compile and print it. Okay, okay, I did not. Oh yeah, my bad. There's another thing you have to do. So we did allocate memory for this outer loop of standard vectors, but this inner loop we have not yet done that. So before doing this line, right, you have to run p of. So yeah, what we did is the outermost loop. Okay, sorry, I'll just write it fresh. So the b vector is now resized to be n. Okay, so the ith loop now can run. So b of any of the ith element is now itself a standard vector. So we can resize them. Okay, so the b of I here is not the integer element. Okay, remember b of I is the standard vector of integers. This is the data type. Okay, so each of these such vectors we can resize it. Okay, to be what? To be of m, size m, because this is what we want to the inner vectors to be. Okay, so you allocate the memory there first, and yeah. So you first allocate the memory for the outermost loop, then innermost loop, and then innermost, and keep going. So I think you can sort of figure out what if I want to do a 3D vector array. Okay, what will that look like? So the resizing of the second index is the first index, the second index, and then you fill the values. Okay, and this is printed. And this should fix this issue. Okay, yeah. Since this is done correctly. So ij starts with 0, keeps going till 14. Because this is 3 cross 5, I guess. Yeah, 5 cross 3. But when again, depends how you look at it. So m, what I do here is that what I did here is that m is the innermost. So I said this is innermost index. So and if going by the C++ or C, how do I put it? The um, convention, it has the row major format. So every row is of size m, okay, and there are 3 such rows. Okay, so 5 columns, 3 rows. Okay, uh, let's extend the same thing. Okay, very similar to this. Let's extend it to the 3 dimension. Okay, so I guess you guys can guess instead of standard vector of integers in the template here, you put another standard vector of integers. Again, you have to resize. Okay, so I had this PQR indices, right? So PQ and R. So outermost P. So let's have that here. Next loop, integer I equal to 0. I less than the size of the next inner more loop. So it will be, oh, sorry about that. It should be P only, the outermost only. So it's P I plus plus, and then you access PFI. Okay, you resize that guy. So resize it to be the the inner loop one. So this Q. You have to write another loop again because you have to initialize the next inner loops. So it actually requires 2 loops here, which will be J. Okay. It should be the iteration for the outermost is P. The next one should be Q. Okay. and then to resize, you access I, you access J, and then resize to be the value R. Okay, so this three structures should take care of all the allocations. First the outermost, then the inner loop, then the innermost loop. Okay, so P, Q, and then R. Finally, we need three loops to index this guy. So I will take three loops. So I with going till P, J till Q, and extend this, have K, that which is goes till R, okay, and access these values. So accessing is sort of straightforward. You have I, J, you have IJK, okay, which stores the value. Again, remember the fastest most index is K. So K plus plus J plus I. Now we'll put the coefficients. K doesn't have need to have any. J will have size of K, which is R, and I will have the size of J and R. So J is Q, so Q times R. Okay. Now let's print this whole thing. Let's print has this. Okay. So let me just comment this and comment this. Okay. Which will have C I J K. Okay. C here and then K. All right. Awesome. Let's print this. Okay. So that worked. If you see the values of PQR, they are 2, 8, and 7. So 8, 7 times 56 times 212. You'll have values till 101, 111. Okay. Okay. So this is how you deal with n-dimensional arrays in the vector format. Again, uh, not the recommended way of dealing with vectors. If you can just linearize it, that's what we saw here. Sorry, not this. Yeah, something like this. You can just linearize it, right? So finally, instead of array, you can just do a vector, dynamically resize it, and pretty much all this code remains the same. If you know the total size, you can give first allocate the complete memory and then revisualize as you want. Okay, you can definitely do it the same exact same thing, yes. Okay, but the reason to show you guys this is that the standard vector class is quite flexible. It can, because it's templatized. Okay, so it does not only take inbuilt data types, which are like integers. Okay, it can actually take custom data types, which is the class itself. Okay, like specifically the integer version of that class. Okay, you can keep chaining it, keep going for higher and higher dimension. Okay, from performance perspective, this is not recommended because it is sort of like a linked list, if I may say so. So technically speaking, this n-dimensional vector, while you n-dimensional array here, okay, it was still a list. Okay, it had contiguous memory layout. The vector class with these high dimensions, they're not exactly a list. They're more like a linked list where you're jumping in memories from one, uh, like a list of vectors. Let's say this is a standard vector of, let's say, this is n, right? So let's say this is 10 vector. I forget how much is that. Okay, 3. So 3 values and such, there are 5 vectors of such. So the first of 3 values is stored in some memory. The next 3 values are stored in some memory, other location. And as such, there are 10 memory locations, which are the starting point for each of these 3 values. Sorry, not 10, 5. Okay. Because you have to actually jump around when you're accessing B of ij, okay? After every third value, you have to jump. That is expensive, okay? And this is what a linked list actually does. So what we actually did is implementation of linked list. Okay, I'll just make a note here. This is a linked list. Okay, you might have seen the implementation of linked list using pointers. This is just using the vector class, how one can implement a linked list. Okay, again, from performance perspective, it's not needed again, because we're using like sort of relying on continuous data type, like what we did here, just to store values. Uh, this whole roundabout way of doing things is not really required. Okay, and again, hurts the performance also. Okay, right. Yeah, question. Don't get this. Why are we resourcing inside the loops? Oh yeah, that's a reason for that. Let's look at this time. Okay, so here, okay, maybe I should do it this way for more completeness. So a dot resize and m given m. So this declares the vector a. Okay, but I did not pass any sizes. Yet. Here I pass a size m to resize it. So that what this makes it is it resizes the vector to some allocation. It allocates memory for it. And because for me it's a single dimensional array, this is fine. This is standard. Okay, this is what we saw. But let's take example of B. B itself is a standard vector. Okay, which is also which itself is also a standard vector of integers. Okay, so the B itself, okay, has n, or where n is 3. So what's the size of B? It's 3. But what are those 3 values? They're not integers. They're standard vectors themselves. Okay. So B has, maybe I'll write it here. B has 3 standard vector of integers. Okay. And what does each of these standard vectors size? It is m, which is 5. And each of these standard vector of integers, okay, is of size 5. Meaning B will have 3 standard vectors, okay, and the each standard vector will have 5 values. Okay, so 5 values in the first standard vector, in the next 5 values, the next standard vector, and so on. Like, and then the next 5 values in another standard vector. So B is essentially a collection of these 3 standard vectors. Now, for the outermost, when we do the dot resize, we resize it to n, which is 3. So the first, it just says that my B can hold 3 standard vectors. That's it. But the standard vectors themselves, we have not resized them. Okay. So then you still have to resize them, right? So that's what this loop is for. So we just run a loop for n, and then going through each of the standard vectors, okay, which is uh, the size n here. So for us, it is 3. And each of these standard vectors, now we are resizing to m, which is 5. Okay. I hope the doubt is clear. Do you get this? Okay. Okay. Straightforward for extend. Yeah, sure. Yeah. Straightforward, extending the same thing to higher dimensions. Okay. When you have standard vector of standard vector of standard vector, essentially, if you think about it, you have to resize each of the loops then. First the outermost loop, then the innermost, then the inner loop, and so on and so forth. In these 3 uh, cases, so because we were able to resize all the dimensions, now I can start accessing the values here, like in this similar fashion, and then print it. Okay, all right. Right. Any questions? So we'll uh, sort of stop here. And if you guys have any questions, I can take them. Yeah. In the next class, we'll start with classes and objects. Yeah. Right. That's a good question. Um, if we have continuous contiguous data layouts, right, it doesn't really make sense to use this. Again, one can use this to visualize, yes, but if you have integers, you can always linearize it and chop it in any way and visualize for yourself in any way you want, like we saw before. Um, but the power of this format actually lies in using custom formats. So, for example, what if you did not pass standard vector of standard vectors? Okay, what if you did something like this, where it is not this guy, okay, it is your custom namespace, okay, in some of a custom namespace, your class, I'll call it my class, okay, that's it. So my class objects will be stored, okay, in a vector format. So what I can then do is I can create different my objects, like whatever objects of my class. This might be little uh, how to put it, difficult right now because we've not covered classes. But then again, just think of like you want to store some kind of user-defined classes which are not standard. Okay. Uh, so 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 the my class objects will be like different uh, object concepts. Okay. But to keep actually a collection of it and iterate them over in a very uh, easy fashion, you can think that way. So what I can then do is b of I will access my ith object. And on top of that, what I can then do is access some very user-defined functions. So let's say b of I, okay, user function like this, and maybe let's say pass some value, which itself may be a function of uh, I or something like that. Okay, they can do complicated or sophisticated stuff like this, right? Yeah. So in those cases, this is actually quite useful, right? I hope this answers the question. That's a good question. Yeah. What I want to you guys to focus on is, yes, we did use user-defined formats like integers and so on and so forth, but the power of these vector classes, because these are templatized, okay, it lies in that it can be extended to even custom data types, or which are like classes in some namespace or something. Okay. Any other questions? If you guys have any questions, feel free to unmute yourself and ask. Yeah. So the raising hands also is fine, but yeah, again, just put in the chat or unmute yourself and ask. That's also I did not get it. Integer standard for void in statement. And I did not get. Can you rephrase it? Yeah, go ahead. Yeah, do you have, I did not get your question, so can you repeat that? Yeah, thank you for the encouraging words. Yeah. About void data types, if you're asking like, can you have void stored here? Actually, that is something, again, um, we don't know the data type of the values they're storing. That becomes difficult, right? What do you mean by accessing values in that case? So that gets tricky. Yeah. So yeah. Another thing is, you're asking about void data types. We will be encountering them through pointers. Okay. They have their own useful cases, like usefulness. So yeah. If I don't know if that answers the question. Yeah. Uh, okay, sure.
Hello,
Yeah. Hi. Go ahead.
sir. I wanted to talk about. Can you repeat the heap in C++? Like what is heap and how it is used?
Yes. Okay. So the way to think about it is there is a syntax of saying to the compiler. Okay. To or OS in general, how you want to think about it. Essentially, to tell the code that the developer or the coder wants the data to be in a certain way. Okay, the syntax for it is using the new keyword. Okay, now why do you want that and all? Reason being, if you want specifically to for your data, like let's say A here, which is some pointer, or B here, okay, which is point to some block of data, right? So that block of data, I want it to be specifically allocated on the heap. as in on the RAM. So that's when I use the new keyword. So this is just a syntax for it. Okay, and then you have to delete it because you manually asked for memory, so you should manually create. That's all. That's what it does. The use case for it again comes from fact that uh, I might require data which is a large amount. So I want my data to be actually stored on the RAM. Okay. So in those cases, you actually use this. It's possible that you might want to have small data. Okay, it's not very large in number, and you want to get the speed of it because if it's small enough, it can fit in cache, and you want to access it frequently. So that's when you use stack allocation like this. Okay. C++. So this is the C way. Okay. C++ provides a very nice class itself. Okay, a very nice way of accessing this, or to be more precise, allocating this memory. Okay, so that's the standard array. This is for stack allocation. The very nice thing about it is you just give the data type, you just give the sizes, and you're done. You do not need to worry about freeing this or how does it allocate the memory and all. You just know that because it's array, I'll just give its data type, I'll give the size, okay, and then I'm done. Okay, if it's a vector, then it will be dynamically allocated. Either I can pass a size during construction, okay, while actually creating the vector, or I do not construct it, but I can just resize it later on. Okay, this makes sure that it will be allocated on the heap or on the RAM. Okay, and this will be staying on the cache. Okay, that's the main difference. To not worry about manually allocating and deallocating, C++ provides this nice way. If you want to do it manually, you can do using the new keywords and delete keywords. That's the only difference. There is performance-wise, there's honestly no difference between using new and delete manually, like manually allocating and deallocating memory, and just using the vector class. Yeah. Okay. Well, to be fair, this is just allocating integers of 20 values. Okay, a contiguous block. So yeah, that's short of it. Yeah. Okay. Somebody asked about recapping the session, so I guess this basically covers what we covered today. About constants, essentially, the extra thing you're telling about your variable is that it needs the value that it contains does not change during the course of the program run. That's sort of the idea here. And we saw about vector n-dimensional vectors where you can sort of create a linked list. We did focus on only integers, okay, final at the final end, and we sort of stacked, or you can think of like we sort of chained vectors on top of it to make one-dimensional, two-dimensional, three-dimensional vectors. Okay, but nothing stops you from making more uh, like high-level vectors or like this with custom namespace classes also. You can absolutely do this. Okay. I hope that clears it out. Awesome. I hope you guys enjoyed the class. Yeah, thank you. Yeah. Yeah. Thank you everyone. So again, before we close off, uh, this is something I always keep telling. The best way to learn is actually coding. Okay, so keep coding, keep practicing this concepts. The If you write the code and actually compile, that's when you actually learn the idea behind it. Okay, like you saw, I while writing it, you make a mistake sometimes, right, and it throws an error. Then you try to understand why did it actually throw it. So it's all correlated that way. The more you write the code, the better you understand. Okay, right? So practice. That's the key thing. Yeah, sure. Yeah, it might get little how to put it, might get overwhelming if you're not familiar with some of the concepts. But then again, that's how you keep at it. You have to just put the time and effort. Yeah. So because we'll be covering the more modern features of C++ from next class. So yeah, the I would say the overload maybe I would say overload, the concepts will keep stacking up. So you have to keep practicing. So the first those two classes were more or less the uh, covering the basics and basic concepts, the foundations, so that you guys are on the same page. Yeah. All right. Okay. See you guys next week, next Monday. Okay. And happy coding.